polynomials. In this video we will discuss generating function for Legendre polynomials. So we will prove that the function 1 upon root 1 minus 2xt plus t square, this is generating function for Legendre polynomials. Generating function means this function can be written as an infinite sequence from 0 to infinity t raised to n p n x, means the series in which p n x acts as coefficients of the nth power of t. The series where p n x is the coefficient of nth power of t, that series, sum of that series is equal to the function 1 upon root 1 minus 2xt plus t square. This means this function on the left hand side, this is generating function for the Legendre polynomials, because in the series we are using Legendre polynomials p and x. So we will prove this. So we can write here 1 upon 1 minus 2xt plus t square. This is called generating function for Legendre polynomials. So now we prove this function is equal to this series. So let us start from 1 minus 2xt plus t square raised to minus 1 by 2, means this function 1 upon root 1 minus 2xt plus t square. So this can be written as 1 minus 2x minus t into t raised to minus 1 by 2, which further can be written as 1 minus u raised to minus 1 by 2, where u is 2x minus t into t. Now we expand the binomial series of this 1 minus u raised to minus 1 by 2, which is 1 plus 1 by 2u, 1 by 2, 3 by 2 divided by 2 factorial, u square, then 1 by 2, 3 by 2, 5 by 2 divided by 3 factorial, u cube, and so on. Now if we simplify this, we will get 1 plus 2 factorial divided by 1 factorial square into 2 square. This term 1 by 2 u can be written like this: 2 factorial, 1 factorial square, 2 square into u, plus the next term, here we have 1 into 3, so we multiply with 2 and 4, which will become 4 factorial, and since we have multiplied with 2 and 4, so we have to divide. That means 2 factorial whole square into 2 raised to 4. Similarly, the next term can be written as 6 factorial, 3 factorial square, and 2 raised to 6 u cube. So we can generalize all the terms of this series in this way. Now we put the value of u, which is actually 2x minus t into t. So this becomes 1 plus 2 factorial, 1 factorial square, 2 square, 2x minus t into t, plus 4 factorial, 2 factorial square, 2 raised to 4, 2x minus t whole square, and then t square, and so on. We will get the general term of this series, that will be 2n minus 2r factorial. We will calculate the n minus r term, so it will be n minus r factorial whole square, then 2 raised to 2n minus 2r, then 2x minus t raised to n minus r, t raised to n minus r, then and so on. So now we have the term corresponding to 2n, that will be 2n factorial, n factorial square, 2 raised to 2n, 2x minus t raised to n, t raised to n, and so on. So now in this series, now we have 1 minus 2xt plus t square raised to minus 1 by 2 is equal to this series, this sum. But we have to prove that this function is equal to t raised to n into pnx. So on the right hand side of this, we have coefficient of t raised to n as pnx. So pnx is the coefficient of t raised to n. So if we prove the coefficient of t raised to n in this series, that is equal to pnx, then our result will be proved. If we prove that coefficient of t raised to n in this series, that is equal to pnx, because we have calculated the value of pnx already, then the result will be proved. That is, this function is equal to summation of these type of terms. So we will calculate the term containing t raised to n in firstly this product, 2x minus t raised to n minus r, t raised to n minus r. So the term in t raised to n in the product 2x minus t raised to n minus r into t raised to n minus r, that is actually this. So we take t raised to n minus r as such, and we calculate the binomial series for this function 2x minus t raised to n minus r, and that will be n minus r cr minus t raised to r and 2x raised to n minus 2r. So it will be n minus r factorial upon r factorial n minus 2r factorial into minus 1 raised to r, t raised to r. Now here t raised to r, here t raised to n minus r, that becomes t raised to n, into x raised to n minus 2r and 2 raised to n minus 2r. So the term, the coefficient of t raised to n in this term, that will be n minus r factorial upon r factorial n minus 2r factorial minus 1 raised to this, x raised to this, 2 raised to this. Or we can say the contribution of this term to t raised to n in the series now contribution of this term. So let us take only this term. We have this series 1 plus this and so on. So we take this term 2n minus 2r factorial n minus r factorial square 2 raised to 2n minus 2r into this. So we have calculated this factor, and this factor is equal to n minus r factorial this and so on. So contribution of this term to the coefficient of t raised to n, that will be contribution of the term 2n minus 2r factorial n minus r factorial whole square 2 raised to 2n minus 2r 2x minus t n minus r and t raised to n minus r. Contribution of this term to the coefficient of t raised to n is 2n minus 2r factorial, that is this thing as such. Now n minus r factorial is here, so here n minus r factorial, so that will be just n minus r factorial, then r factorial, then 2 raised to 2n minus 2r, so here we have 2 raised to n minus 2r, so it will be just 2 raised to n, then minus 1 raised to r, then x raised to n minus 2r. So this is the coefficient of t raised to n in this term only. But we have to calculate the coefficient of t raised to n in all the terms. So that will be, if we take the sum, so summing, because all the terms are of this type, 1 plus this plus this plus this, so all the terms are of the type summation n varying from 0 to infinity, such n varying from 0 to infinity of the type 2n minus 2r factorial, n minus r factorial, and so on. So we will sum all these terms for r varying from 0, 1, 2 up to n, where this capital N is basically n by 2 or n minus 1 by 2, whichever is integer, because r goes up to n by 2. So if n is even integer, then capital N is n by 2. If n is odd integer, then it is n minus 1 by 2. So contribution of whole the series to the coefficient of t raised to n is, so we get that coefficient of t raised to n in basically this function 1 minus 2xt plus t square raised to minus 1 by 2 is summation r varying from 0 to n minus 1 raised to r 2n minus 2r factorial 2 raised to n, all this term r factorial, n minus r factorial, n minus 2r factorial into x raised to n minus 2r. Here n minus 2r factorial also. This n minus 2r factorial. So this is basically Pnx, which we have calculated earlier. So now we have proved coefficient of t raised to n in this term, that is equal to Pnx. Therefore we can say that 1 minus 2xt plus t square, because we know this is a series which contains terms containing powers of t, and we know coefficient of t raised to n in this function, that is Pnx. So we can write this is just the sum of t raised to n into Pnx from 0 to infinity. That means this function is generating function of Legendre polynomial. Now this function is called generating function of Legendre polynomial because the Legendre polynomials can be obtained by this generating function. So now let's take some examples. Now we have to prove that Pn1 is equal to 1. Actually we have calculated the value of the constant in Rodrigues formula by using Pn1 is equal to 1. But now we have to prove Pn1 is equal to 1. So we will substitute x is equal to 1 in the generating function, because we know 1 upon 1 minus 2xt plus t square, this is equal to summation Pnx Tn from 0 to infinity. So if we put x is equal to 1, then the left hand side becomes 1 upon 1 minus t. When we put x is equal to 1, this thing becomes 1 minus 2t plus t square, which is square of 1 minus t. So this term becomes 1 upon 1 minus t. And on the right hand side we have Pn1 t raised to n from 0 to infinity. So therefore we can say that summation Pn at 1 t raised to n from 0 to infinity, that will be just 1 minus t raised to minus 1, and that is just 1 plus t square and so on up to t raised to n and so on. So now in the left hand side the coefficient of t raised to n is Pn1, and on the right hand side the coefficient of t raised to n is 1 for every power n. That means Pn1 is 1 for all n. If we compare all the coefficients of all the powers on both sides. Now next example we have Pn minus x. This is minus 1 raised to n Pn x. Legendre polynomial of order n at minus x. This is minus 1 raised to n into polynomial Pn at x. So again we will use the generating function to prove this. We will replace x by minus x and t by minus t in the generating function. So let us say this is equation 1. So we will replace x by minus x and t by minus t in equation 1. So left hand side will be still same, and right hand side becomes Pn minus x and minus t raised to n. So it will be summation Pn minus x minus 1 raised to n into t raised to n from 0 to infinity. And the left hand side, that is the generating function for the Legendre polynomial. So this is basically summation Pnx Tn. So this left hand side is equal to this, and right hand side after simplification becomes this. So on the left hand side the coefficient of t raised to n is Pnx, and on the right hand side coefficient of t raised to n is minus 1 raised to n into Pn minus x. So comparing the coefficients on both the sides, we will get Pnx is equal to minus 1 raised to n Pn minus x. So this we want to prove. Now from this example we can also calculate the value of Pn at minus 1. Now value of Pn at minus 1, that will be just Pn minus 1 raised to n into Pn at 1. But Pn at 1 we know that is 1, so this is just minus 1 raised to n. So Pn1 is equal to 1 for all n, and Pn at minus 1 is equal to minus 1 raised to n for all n.